Hi, this is section 1.11 on dipole moments and molecular polarity. Your book has a section on this, which is what we're going off of, and the language it uses is pretty decent, and I could recommend you to read it to try and increase your knowledge on this subject, especially because it could be on the test. What we will do, though, is that I will give you a rundown in my own words of what is worth looking at in this chapter. That way you can have um, two different types of instruction here. So to do that, let's go to our notebook. When your book talks about dipole moments, they talk a lot about the mathematical relationship of a dipole moment and the physics terms around that. So mu here is the dipole moment, and delta here we've seen before. This is the partial charge on some atom, and d is the distance between the two atoms that we're talking about with the dipole. So for instance, if you had a carbon and a chlorine, the partial charge on the carbon could be used as delta, and the partial charge of chlorine could also be used on delta if you wanted. They should be relatively similar. You'd imagine that the amount of electrons pulled towards the chlorine is equal to the amount of electrons pulled away from the carbon. And the distance, of course, would be, let's see, the distance would be equal to this bond that they share. And you could calculate the dipole moment, but what you probably should just take a second to note is that as the partial charge gets bigger, the dipole gets bigger, and as the distance across a molecule gets larger, so does the dipole as well. So these are the main things to take away from the dipole moment formula that is presented in your book. But dipole moments are a lot more than just single bond entities, because, for instance, let's say you have this molecule. You have carbon bonded to a bromine on one side, a bromine here, and the other parts of the tetrahedron are hydrogens. Now it gets a little complicated because you could imagine there's a dipole between the carbon and each bromine, but there's also a dipole between the hydrogen and the carbon, right? So because of both of these dipoles, there's actually a molecular dipole that exists. Because if you notice, the dipoles kind of all point in the same direction. And that overall direction is sort of in this direction, right? It's sort of from over here up this way. So that means that the overall molecule has a dipole that is different than the smaller dipoles that make up or that are formed from each individual bond. And these molecular dipoles can influence how a molecule acts, how it reacts, and what it is soluble in. So if we take another example of a molecule, let's instead draw something like this. Carbon tetrafluoride. Fluorine is the most electronegative atom that we have on the periodic table. And as such, each of these fluorines are going to pull electron density away from this carbon. And while that should be, oh, whoops, I drew this one backwards. Sorry. And while this should be very strong and there should be a very high dipole moment, if you notice, this dipole that I've just highlighted and this one cancel each other out. They're equal magnitude going opposite directions. Also, if you notice, this dipole and this dipole cancel each other out. So because of that, the dipole moment of this molecule is actually very, very low and would be much lower than the example with bromine that we just did a second ago. And that's because if the molecule is symmetrical and you have the same dipole pulling in two directions, they cancel out, as we just saw. And so the dipole here would be extremely low for the carbon tetrachloride, whereas the other one, the bromine one, would be much higher. And we can also rank dipole moment. In your book, there's a table in 1.5 where they give a little more detail into precise dipole moments for a whole bunch of different molecules. But for now, that's what you need to know, is that you can have net dipole moments across a molecule, as we did here. You can have net dipole moments that cancel out to give you no overall dipole moment. And you can also have singular dipole moments across a bond. So this has been section 1.11.